They have to hit them with a mic.
Okay, welcome everyone. Good morning. Welcome to the MGH Neurology Grand Rounds. Today we have Dr. Christian Badr, PhD, who is an associate professor in neurology at Harvard Medical School and a principal investigator in the Department of Neurology at the Massachusetts General Hospital. He obtained a master's in cell engineering from Henry Poincaré University in France and a PhD in molecular biology from Ria University, Amsterdam. He did his postdoctoral training at MGH. His lab focuses on studying the genetic drivers of malignancy and treatment resistance in glioblastoma stem cells and developing targeted and experimental therapeutics for high-grade gliomas. Let's welcome Dr. Badr.
Thank you so much, Mia. Good morning, everyone. Thank you all for being here. It's a real honor to be in this room and to be talking about our work. So the title of my talk today is Stress Signaling in Glioblastoma Pathogenesis, Metabolism, and Response to Therapy. I have nothing to disclose. So glioblastoma, or GBM, it is the most common primary brain tumor in adults. It's the deadliest type of brain cancer. This year alone, there will be over 14,000 Americans that will be diagnosed with GBM, and over 10,000 will succumb to this disease. The five-year survival rate for GBM is less than 7%. And the median survival in GBM patient is roughly 14 months. Currently, the treatment for GBM consists of surgery, radiation, and chemotherapy with temozolomide or temodar, which is an alkylating agent. The problem is that the survival rate and the statistics for GBM has not moved in over 2 decades. Essentially, the biggest advance in the field was the introduction of temozolomide in the early 2000s. And what you see here on the left is the Kaplan-Meier's curve for survival of patients that were treated either with radiotherapy alone or with radiotherapy with temozolomide. And there is an increase of a few months. But since then, there's really haven't been anything significant. Probably the most notable is the introduction of tumor treating field, or TTF. Essentially, this is a helmet that the patient has to wear. It induces low potency current to try to kill the tumor cells. And essentially what this does is really increase the survival by near 4 or 5 months. But also there's a lot of negatives to this therapy. For example, the patient has to wear this helmet and carry the battery on them at all time for roughly 18 hours or longer during each day. And this comes at a whopping cost of around $21,000 a month. So needless to say that there has been very limited progress in the treatment of GBM. In my lab, we are mainly focused on glioma stem cells, and we study the tumor plasticity in this disease. And I'll try to explain to you why is it important to look into that. So gliomas are members of the brain community. And within this community, there's both a cooperative and competitive behavior, be it between the tumor subclones or between the tumor cells and their environment. And as it is the case in evolution, the ability of species or cells in that case to adapt to the most microenvironmental changes or stresses is linked to being conserved evolutionarily and is linked to survival. And the cells that are the most adapted with such capabilities are the glioma stem cells. So these cells have the plasticity, and I'll show you it's not only a genetic plasticity, but it's also a metabolic plasticity. And by definition, glioma stem cells are able to self-renew, they can differentiate into multiple lineages, and they can initiate tumors at any given moment. So because of this plasticity and the common heterogeneity that occurs in GBM, there is therapeutic resistance, and therapeutic resistance inevitably will lead to tumor progression. And we believe that it's really critical to identify the mechanisms that are responsible for this glioma stem cell plasticity. So how these brain tumor stem cells regulated in the brain? There are multiple factors that can drive tumor initiation, tumor progression, as well as recurrence. However, a lot of these factors, they also cause a lot of stress on the tumor cells, and particularly on the glioma stem cells. For instance, if we take external factors such as the biochemical environments where these cells reside, we know that glioma stem cells reside in hypoxic niches. So in this environment, microenvironment, there's low oxygen, there's high level of ROS, it's acidic pH, low nutrients, and all these factors combined induce a lot of stress on the tumor cells. There's the therapy as well, for example, temozolomide, radiation, and other targeted therapy, they all induce a stress response on the tumor. In addition to all these external factors, there are also cell autonomous or intrinsic factors, such as oncogenic stress, genomic instability, and the high rate of protein synthesis. And they all contribute to the stress signaling in the tumor. Yet, despite all of this, the glioma stem cells are capable not only to survive, but actually to thrive under such a hostile environment. So that's why we set out to study the role of stress signaling in both in plasticity as well as in survival of these glioma stem cells. So basically, the cells respond to stress through two major signaling pathways. One of them is the unfolded protein response, or UPR, which is usually activated by ER stress, and the integrated stress response, or the ISR. And the role here is whenever they're stressed, these cells activate these two responses in order to restore homeostasis. And this is mainly done through an adaptive translational reprogramming. So basically, there's a decrease in global mRNA translation, and there's an increase in translation of a certain subset of mRNAs. And what happened here is that whenever there's a mild or short stress factors, these cells activate a pro-survival response. This allows them to overcome the stress and survive. However, when their insults are really intense or prolonged, the cells can no longer cope with the stress, and instead they would activate apoptosis. And some of you in the audience might be very familiar with these signaling pathways because ER stress and the ISR activation, as well as the resulting mRNA translational defect, are very common in a wide range of neurodegenerative diseases. For example, Huntington disease, Alzheimer's, tauopathies, etc. They all have this common problem, which is the activation of the stress, and particularly the ISR. And this actually leads to the generation of specific neuronal populations. So there are multiple evidence that the ISR is actually activated in GBM. For instance, if we take the three main constituents of the ISR, meaning ATF4, CHOP, and GAT34, if we probe the cancer genome atlas data for mRNA expression of these three genes, what we see is that there's a gradual increase of the expression of these three genes as the tumor becomes more and more malignant. Basically, from grade 2 to grade 4, grade 4 is the GBM. These cells have the highest level of mRNA expression of stress markers. We can look at this differently. There's seminal work by Mario Sula's lab here at MGH a few years back. They defined four molecular states in GBM: the oligodendrocyte progenitor-like, the neural progenitor-like, astrocyte-like, and the mesenchymal-like. And these mesenchymal-like cells, who tends to be very aggressive, they are most influenced by the tumor microenvironment. And when we look into the gene expression that define these particular cell population, what we see is that there's a lot of ATF4 target, and there are genes among these that are known to be activated by stress. So this is additional evidence that the ISR is actually active in GBM. So throughout my talk, I will try to answer these three questions. First, we know that physiological stress must be controlled, otherwise it becomes cytotoxic. So how come these tumor cells are able, or how can they control the stress signaling? The second question, how does this stress signaling impact the response to GBM therapy? And how does stress signaling provide survival, or does it provide any survival advantage for GBM? So as I mentioned earlier, whenever there's an excessive or prolonged ISR activation, this is detrimental and the cells will die. And that's, again, an example. It's a common problem in degenerative diseases. Yet we know that the ISR is activated in GBM. So how come these glioma stem cells can overcome this? Unlike other brain resident cells, these glioma stem cells are really well at overcoming this stress response and even thriving under such conditions. And one answer to that is there must be some adaptive mechanism to counteract such activation. And And these mechanisms are likely essential for proteostasis as well as the tumor growth. And we also know that translation is global translation is actually not impacted in GBM. In fact, it's quite the opposite. GBM cells have a very active translational mechanism, and they synthesize tons of proteins. So when we wanted to look into this, we looked into EF2B, and mainly because the translational initiation is tightly controlled by this protein complex. So basically, EF2B has to be active in order for translation to initiate and to occur. It is important to mention that EF2B activity could be modulated through two different ways. One is by increasing the total amount of this protein available. For instance, has been shown that the epsilon subunit in this complex, called the EF2B epsilon, is encoded, which is encoded by a gene called the EF2B5. Whenever this is upregulated, the EF2B complex becomes active. Another way for modulating this complex is through phosphorylation. Essentially, phosphorylation, the EF2B epsilon can inhibit this protein complex. This is one thing we have not looked at because we don't have any tumor tissue. So if there's anyone who has access to GBM tissue, we would love to work with you on this one. But essentially what we did, we looked at all the 5 genes that constitute this protein complex, essentially EF2B1, 2, 3, 4, and 5. We did not see any significant upregulation in the TCGA data sets of any of these genes, nor any correlation with poor prognosis. However, when we look whether there's any amplification or deletion in these genes in GBM, we found that in 2.5% of glioblastoma patients, there's an amplification of the EF2B5. And when we compared survival of patient who has this tumor amplification versus the unaltered group, we saw a huge difference in overall survival. Essentially, the unaltered group has a 14-month survival, which is the average survival in GBM in general, whereas those who have amplification EF2B5, it's only 7 months, so it's cut down in half. That was a really strong and striking difference in survival. So we wanted to know exactly what is going on. And as I mentioned earlier, one way to activate this complex is by overexpressing EF2B5. That's what we did here. And essentially what we saw is whenever EF2B is activated, there's a universal resistance to any clinically relevant therapies. What's shown here are cells, glioma stem cells, either expressing the control factor or overexpressing EF2B5. These are treated with different either targeted inhibitors such as EGFR inhibitors, AKT2 inhibitor, mTOR inhibitors, all the standard of care therapy, which is either temozolomide or radiation. And red is the cells are dead, white or blue are the cells are alive. And essentially what you see is that whenever you overexpress EF2B5, these cells become resistant to any therapy that we give to these. We can also activate the EF2B5 through pharmacologically by using 2 different inhibitors. And here again, you see the same thing. Whenever EF2B5 is activated, these cells become resistant to this treatment. The opposite is also true. If we take cells that are inherently resistant to EGFR inhibitor or to temozolomide or radiation, we knock down the EF2B5, and these cells now become sensitive to these therapies. So the question here is, can glioma stem cells adapt to stress signaling that's either induced by the tumor microenvironment or induced by the therapy through regulating EF2B activity? And this is something that we're actively pursuing right now at the lab. So I talked about the the ISR, and what about the ER stress? Here we looked at BIP. BIP is an ER chaperone, and it's the central regulator of ER stress. What you see here is that in GBM patient BIP expression is upregulated equal to the normal brain. And patients whose tumor express high level of BIP tend to have shorter survival compared to the low expressors. This is this is just a cartoon showing our basically our in vivo mouse models. Basically, we take these GBM cells from patient tissue. We grow these cells under conditions that would enrich for the glioma stem cells. These cells now grow as neurospheres, and we can tag them, for example, with sprays and implant them in the brain of mice, and they will form tumor. That's how we study GBM in mouse models. What you see here is that in a control group, when we implant these cells, they all engrafted, they all form tumors. However, when we knock down BIP and we implant these cells in the brain of mice, they are unable to form any tumors at all. So what this tells us is that BIP is essential for tumor growth and is also a prognostic factor for GBM. We can also see this differently. So if we take a panel of patient-derived glioma stem cells, we can see that some of them express high level of BIP versus low levels of BIP. And if we take one that's low BIP versus high BIP, we implant these in the brain of mice, you can see there's a huge difference in survival. Of course, I'm not saying here that BIP is actually driving this aggressive phenotype, but BIP is definitely a reliable factor for looking at prognostics or aggressive tumor aggressors in these tumor types. But a better way to look at this is looking at intratumor heterogeneity in terms of stress response. A few years back, we published a paper where we defined what we call a floating cell population. Essentially, within any patient-derived glioma stem cell line, we can isolate a subset population that are much more aggressive. We show that these cells have a more Zankov signature, they are more resistant to common therapies. And these cells are enriched under hypoxia or acidic pH. Of course, these conditions are known to activate ER stress. And when we compare stress signaling, so NS are the neurospheres, so this is the parental population, FC are the floating cells, and this is the subset population that is more aggressive. And you can see clearly that the ER stress markers are increased in this aggressive population. Again, these cells are more tumorigenic in vivo. So I mentioned that stress signaling might be promoting GBM survival or activating tumor growth. So one thing we found early on is that ER stress actually activates a pathway called lipogenesis or de novo lipid synthesis. And as the name indicates, this is the main pathway through which cells can convert citrate into lipids, fatty acids. In this pathway, the final enzyme here is called SC1 or enzyme A desaturase. As the name indicates, it's a saturase enzyme which converts essentially saturated fatty acid, palmitic acid, stearic acid into unsaturated fatty acid, mainly palmitoleic acid and oleic acid. And what is shown here is that whenever we activate ER stress using a chemical compound called topsygorgin, there's a strong upregulation of all these enzymes that belong to this pathway. And this is a dose response based on the dose of topsygorgin that we give. And the opposite is true as well. If we alleviate ER stress using 3 different chemical compounds, we see a downregulation of SCD. So we mainly decided to focus on SCD1, and the first question we asked whether this enzyme is actually active in brain tumors. And the way to look at that, we implanted brain tumors in mice, and we gave those either a control BSA or P16. Again, C16 is the precursor of SCD. And we take the tumors out, we section them, and we stain them for neutral lipids. And what you see essentially is that the mice that receive this palmitic acid, which is, by the way, very rich in our diet, everyday diet, now these tumors have a very high accumulation of lipids. And that shows that actually this C16 has been actively converted into neutral lipids by FEV1, and that this enzyme is functionally active in brain tumors. This work was published a few years ago and led by Kelsey Pinkham and David Park in the lab. And essentially what we showed here is that whenever there's ER stress, they activate one of the ER stress sensors, which is IRE1, and this in turn activates this lipogenic transcription factor or SRABP. Now, SRABP is responsible for the upregulation of all these genes that I showed this pathway. But most importantly here, what we found is that besides its role and just as a desaturase enzyme, what SCD does is plays a cytoprotective role in brain tumors, actually. So these unsaturated fatty acids that are synthesized by SCD alleviate ER stress and increases survival whenever there's a high ER stress response. We also showed that knockdown of SCD can defeat stem cell properties in glioma stem cells. Most importantly, when we knock down SCD1, these cells are unable to engraft and form tumors in mice any longer. Also, we take glioma stem cells that are high passive. Basically, these cells have been cultured in the lab for a long time. What happens is that they lose their self-renewal ability, so they can no longer form tumors when we inject them in mice. However, if we overexpress SCD1 in these cells and implant them, now they gain back their ability to engraft and self-renew and form tumors. And mice eventually they die because of these brain tumors. We wanted to pharmacologically target SCD1. At that time, we had this compound from Cayman called K1566, or K for short. It's a highly potent inhibitor of SCD. However, the problem is this does not penetrate the blood-brain barrier. And in order to overcome this issue here as a proof of concept, we used intranasal delivery of a Cayman compound into mice. Essentially, this was given through the nose. And what we saw was very encouraging. In one highly aggressive mouse model, we saw that we can double overall survival by giving mice this inhibitor, and 25% of mice actually never formed any tumor even after 6 months. And in the less aggressive tumor, the results were even more encouraging. Essentially, here we saw that all the mice that were treated with this compound were cured, and for up to 6 months showed that there's no tumor at all in these mice. It is important to mention that there are two human isoforms of SCD, SCD1 and SCD5. Even though there are hundreds of papers linking SCD to various diseases in the literature, almost all of these has focused on SCD1. There's only a handful of small studies related to SCD5. And actually, nobody even really knows what is the exact function of SCD5. So this work was led by Haik Natzakanyan in the lab, postdoc in the lab. And essentially what we first wanted to do is look at SCD expression in brain tumor at the single cell level. So this is single cell RNA-seq data from 8,000 cells from 28 different patients. This is just public database, and you can see that they cluster differently based on gene expression. When we look at SCD1 expression, we saw that it's fairly well represented among different GBM populations. However, the problem is that a lot of cells do not express SCD1 at all, and these are the ones you can see in purple here. And essentially, we were not really thinking about SCD5, but we decided just to do diligence. Let's look at SCD5 as well and see what happens. This was very shocking, surprising to us. Turns out that SCD5 is expressed not only almost ubiquitously in all the GBM population, but it's also at much higher levels than SCD1. And so this indicated to us that maybe SCD5 is also important for brain tumors. The problem here is that there is no SCD5 antibody. And another reason why it's so difficult to study SCD5 is it's exclusively expressed in primates. So mice or rodents in general, they do not express SCD5. So it's very difficult to do animals like these. The first thing we wanted to do is generate an antibody for SCD5. And thanks to the heroic effort of Haik, after years, actually almost 2 years of trial and error, we were able to make the first and characterize the first SCD5 specific antibody. Now, not only we can confirm that single-cell RNA-seq data at the protein level, and we did in fact see that SCD5 is highly expressed in GBM, but also we can study the cellular localization of this protein. And what we saw essentially is both SCD1 and SCD5 are localized in the DER mainly. However, the subcellular localization of SCD1 and SCD5 is different. Just like knockdown of SCD1, knockdown of SCD5 is also can kill glioma stem cells, but does not affect astrocyte. And just like knockdown of SCD1, whenever we knock down SCD5 and implant these cells in the mouse brains, most of the mice are unable to form any tumors. To look into the role of SCD5 in lipid metabolism, we wanted to look at naturally fatty acid metabolism and desaturation in particular. And this work was done in collaboration with Stephen Bensinger at UCLA and Sandra Sparkle. Basically, we did what is called shutdown lipidomics. This technique was pioneered by Steve's lab. essentially, it allows us to look at close to 900 different lipid species that belong to 17 different lipid subclasses. And if you just look at this area, so the first column is the control, second column is knockdown at SCD5, third is knockdown at SCD1, and the fourth one is overexpression at SCD5. And what you see right off the bat is that the lipid profile of the knockdown at SCD1 versus SCD5 is not exactly the same. There are a lot of similarities, this area here, and those are the unsaturated fatty acid. So you can see that most of these enzymes are actually required for fatty acid saturation. However, there are lipids that are totally differently expressed in SCD after knockdown of SCD1 or SCD5. So to look more closely into that, we did what's called principal component analysis. And here we're asking the question, what lipids can contribute to this difference between SCD1 and SCD5? And essentially, you can see that there's these lipids cluster in completely different regions, which confirm that there are different roles between SCD1 and SCD5. And what we found essentially is that SCD5 plays a predominant role in phospholipid synthesis. We also wanted to look at this in terms of gene expression. So we did RNA-seq experiment after knocking down either SCD1 or SCD5, using different shRNA. And as expected, we found that things like, for example, inner membrane in the organelles or mitochondria are disrupted, which is very well expected because we know that unsaturated fatty acids are essential for membrane fluidity and for membrane synthesis. However, what was surprising is to see that SCD1 and SCD5 might be also involved in cell division and cell cycle regulation. To get a closer look at this, we did a secondary analysis, or reactome analysis, and we found that indeed SCD1 and SCD5 are important for cell cycle regulation as well as DNA damage repair. This was functionally validated. So what you see here is that whenever we knock down SCD1 or SCD5, there's a G1 arrest. These cells are no longer able to cycle. Also, what's very interesting, when we looked at mRNA or protein expression of SCD1 and SCD5 through the cell cycle, we see that there's a peak in their expression at the end of S phase and early on G2M phase. So this again confirms that these enzymes, although they are essential for lipid metabolism, but also are playing a role in cell cycle. Also here, we wanted to look at DNA damage repair. So we clustered all the genes that are known to be involved in DNA damage. And you can clearly see right off the bat that whenever you knock down, particularly SCD5, there's a huge decrease in all of these genes. SCD1 as well, but it's not that extent. And we were able to actually validate that at the protein level. So here, when we knock down either SCD1 or SCD5, you see increase in DNA damage shown here as phosphorylation of H2AX. PARP, which is important for DNA repair, is actually downregulated. And we see the opposite when we overexpress either SCD5 in particular or SCD1, DNA damage is decreased, PARP expression is decreased. So this work shows that there's an intimate link between lipid metabolism, cell cycle regulation, and DNA damage. And here, this also proves that, as I told you earlier, we showed that SCD has a role, cytoprotective role through control of ER stress. Now, we also know that there's an additional cytoprotective role, which is by controlling DNA damage. Of course, DNA damage is highly important in GBM because all the therapies, mainly temozolomide and radiation, are based on creating double-strand break in these cells and killing these cells by DNA damage. So we wanted to look closely into that. Now, double-strand break repair is a big problem for GBM because these cells are really good at overcoming this. It's basically all the often the chemo-resistant or radio-resistant issues because these cells are able to fix this DNA breaks and overcome this damage. And the DNA damage break repair is done through two different processes. One is called non-homologous end joining, or NHEJ, and the other is called homologous-directed repair, or HDR. HDR is regulated by a protein called RAD51. And in line with the previous slide where I showed you that all these DNA damage repair genes are downregulated when we inhibit SCD1, here as well, we see that when we treat glioma stem cells, three different patient-derived lines, treated with SCD inhibitor, and every time you see that BRAF51 expression is decreased, gamma H2X, again, the DNA damage marker is increased. And the DNA damage is even more obvious whenever we combine SCD inhibitors with temozolomide. So we wanted to functionally validate that again. So HDR is regulated by REST51. And we asked the question, does SCD inhibition really impair homology-directed repair? For that work, it was a collaboration with Charles Day and Taiwan. And essentially, we have designed a few years back a new bioluminescent reporter that can sensitively and non-invasively track DNA damage repair. So we could measure DNA repair not only in vitro, but also in vivo. We call this via our bioluminescent repair reporter. And essentially, what we found is that whenever we treat glioma stem cells with different inhibitors of SCD, we always see a downregulation of this homology-directed repair. So we were able to functionally prove that. This is really important because this, in theory, means that SCD inhibition combined with either temozolomide or radiation should increase the therapeutic response. And I'll show that. So if we pause here for a second, obviously our goal is to find a new therapy for GBM. And we ask, what are the key components to have an effective GBM therapy? First, you need a good target. So I think at this point, we had good data suggesting that SCD could be an effective therapeutic target for GBM. Next, we needed to have a drug that is capable of penetrating the blood-brain barrier and engaging its target in the brain tumors. As I mentioned, the compound that we used initially, although it was extremely potent, it does not penetrate the brain, so it cannot be used in patients. And here we started a collaboration with Humanity Therapeutics, which has since now recently been acquired by Janssen. So Humanity has designed a compound called YTX7739, and that was designed for the treatment of Parkinson's disease. The reason for that is that SCD is also a therapeutic target for Parkinson's. And the short story is because oleic acid, which is the direct product of SCD, has been shown to contribute to the toxicity seen in Parkinson's, the neurotoxicity that's seen in Parkinson's disease. Humanity has already conducted pharmacokinetic and pharmacodynamic studies that show that YTX can actually effectively penetrate the brain in non-human primates. And they had, most importantly, last year, they had completed a phase 1 clinical trial in human subjects where they showed that there's no concerns of toxicity or tolerability issues in humans. So next, we have an inhibitor. We also want to know the mechanism of action. So how is this drug, how and why is it killing the brain tumor cells? And then we also wanted biomarkers that predict therapeutic response, basically which patients are most likely to respond to this therapy. And that's where we engaged in this study, which was led by Katerina Ain and Alessandro Sammarco. And basically, what we did first is characterize YTX7739. What you see here is data showing that this inhibitor effectively inhibits SCD. So here, what we're looking at is the ratios of C16, C18, both saturated and unsaturated. And what this data shows that there's over 70% decrease in fatty acid saturation. So that means that this inhibitor is actually inhibiting SCD. Importantly here, what we see is that whenever we treat TSCs with this inhibitor, we can kill over 90% of the cells. However, when we supplement these with oleic acid, which is the product of SCD, we can almost fully rescue this phenotype. And this is not the case by adding the 16, which is the precursor of SCD. We wanted to further confirm the specificity of this inhibitor. We did a full lipid profiling. And essentially, what we compared here the effect of this inhibitor versus the knockdown SCD1. And we see that all the unsaturated fatty acids are depleted. This is the bottom part here, which is good. So that confirms again that this inhibitor is actually inhibiting SCD. However, surprisingly, what we saw also is that there's a strong accumulation of saturated fatty acids. So those are the fatty acids that are upstream of SCD. Now, it is known that when saturated fatty acids accumulate in the cells, they cause a toxic ER stress response that's known as lipotoxicity. In fact, we confirmed that what we see is glioma stem cells treated with YTX have strong upregulation of all the ER stress markers or DNA damage markers shown here, both at the protein and mRNA level. So just to summarize this, what I told you about SCD so far, essentially, whenever there's a mild or manageable ER stress, the cells will upregulate SCD. So now they're not only disposing of the saturated fatty acids and preventing their accumulation, but they're also making unsaturated fatty acids. Those unsaturated fatty acids are important for glioma stem cell proliferation, and they support tumor growth. And part of those reasons that because, as we well know, that unsaturated fatty acids are important for membrane fluidity, for cell signaling, as well as lipid storage. However, whenever we block SCD, what happens essentially is not only we are depleting those unsaturated fatty acids, but now we are causing this toxic accumulation of these saturated fatty acids that now inducing lipotoxicity and causing this very toxic response to these cells. Essentially, what we're doing is we're poisoning GBM tumors using their own intermediary metabolites. And just to put this into perspective, there are 4 different ways to target lipid metabolism or to target metabolism in general in GBM. The first one is by depleting extrinsic nutrients. So one of the most famous example is the ketone diet, where people have tried to deplete glucose to the tumor. However, this I would argue that this does not work at all. One of the many reasons for this is that now we know that tumors actually can grow independently of glucose. Well, glucose is a very important fuel for brain tumors, of course, but also these brain tumors can get carbon from other sources, including fatty acid oxidation and others. Another strategy is to block the transporters or receptors such as glucose or glutamate transporters on the cell. However, many of these inhibitors don't really work well, and a lot of them cause a lot of systemic toxicity. This strategy has not been successful. The third one is to inhibit biosynthesis of endogenous metabolites, and one could argue that we are kind of doing this here by blocking the unsaturated fatty acid. But also the fourth strategy would be to promote toxic accumulation of metabolites. And this is exactly the example that I showed you about the accumulation of saturated fatty acid when we inhibit SCD. So as I mentioned earlier, we showed a lot of data that proves that inhibiting SCD can impair DNA damage repair, and in theory, this should sensitize to DNA damaging theories. And in fact, what we saw is that whenever we combine this inhibitor with either temozolomide or radiation, we do effectively kill those glioma stem cells. So the upper panel here is a primary GBM. And what you can see is that whenever we combine, these cells respond fairly well to temozolomide. This is the gray bars here. But whenever we combine temozolomide with the SCD inhibitor, we can actually kill most of these cells. Same goes for radiation. This is also valid for recurrent GBM. So this is the patient-derived GBM in recurrent tumor. These cells are fully resistant to temozolomide, as you can see in this image here. However, when we combine again temozolomide with this SCD inhibitor, these cells now actually we can deplete a lot of the spheres. What we are doing here is looking at the secondary sphere formation. So this is looking at the ability of these tumor cells to self-renew and form new tumors. And again, here, same thing that's valid for temozolomide is also valid for radiation. So next, we wanted to go in vivo. And first thing we did is confirm that this inhibitor actually does inhibit fatty acid saturation, not only in the plasma, not only in the brain, but also inside of the brain tumors. So these are mice that have established brain tumors, and we give them YTX. We take the tumor out and we analyze those fatty acids. And not only we see a depletion of fatty acid inside the tumor, but we also see an upregulation of ER stress markers. Again, this is a way for us to know that these cells are being or are undergoing lipotoxicity. And this also is, we also see an increase in apoptosis that's shown here by Cleave caspase. So we tested this therapy in mice GBM model in combination with temozolomide. Again, here the model on the left is a highly aggressive tumor type GBM cell line. And what we see, unfortunately, that YTX alone did not really have any remarkable effect. The increase in survival was only negligible, only 3 days. However, whenever we combine this therapy with temozolomide, we managed to double the overall survival. So that was really, again, this is a highly aggressive tumor and does not really represent a very clinical case scenario. In the second model, this tumor is now less aggressive, and this one responds very well to temozolomide. Again, you can see temozolomide alone did really well, doubled the survival, but also so did the YTX compound. So the increase in survival was roughly 40 days compared to control. And again, here, whenever we combine these two therapies, we get the best survival. What was the most encouraging here to see the long-term survival, essentially looking at how many mice survive after 6 months. In the case of the control, it was 0 because most of these mice died by day 60 or so. In the case of temozolomide, we had 25% mice that survived this therapy. And in case of YTX, it was 37%. So basically what this shows is that this inhibitor almost does as good as the standard of care chemotherapeutic for GBM, which is temozolomide. We also tested this in the brain metastasis model. So we have a different project where we're looking at the effect of FCD in breast cancer. And what we did here is we wanted to mimic the worst case scenario for brain metastasis. Essentially, we take a triple negative breast cancer cell, we inject these cells directly into the brain, and we treated these mice with either YTX alone or YTX with niraparib. Niraparib is a brain-penetrant PARP inhibitor. As I mentioned earlier, we did see that SCD inhibition decreases PARP activity, and PARP, of course, is very important in DNA damage repair. Here again, although the results were not as striking as what we see in GBM, but we did see that whenever we combine these two therapies, we actually get the best overall survival. Okay, so this is all well. However, this is where the problem lies. When we tested this therapy on 12 different patient-derived lines, what we saw essentially is that half of these respond well to the treatment and they die, whereas the other half are fully resistant to therapy. And of course, this is a problem because you cannot give this therapy to a patient knowing that there's a 50% chance that their tumor might not be responsive at all. So this is a really difficult question that we struggled with for over 4 years to try to answer what really makes some cells very sensitive to SCD inhibition, whereas other ones are fully resistant. What you see also here is this is the primary human astrocytes. Luckily, these are the most resistant to this therapy. And after many trials and error, to answer this question, we decided to reverse engineer glioblastoma. Essentially, our starting point was primary astrocyte. As I said, these cells are fully resistant both to SCD, to two different SCD inhibitors, YTX and the gamma compound. And we use this as a very old, 20 years old model where astrocytes can be converted into glioma-like cells. And this is basically what we did here as a step-by-step conversion of these primary astrocytes into more GBM-like. And at each step, we were asking, does this make this cell sensitive to this therapy? The first step here is to immortalize primary astrocytes. We used third and loss function of the tumor suppressor 3 and PRB. And anyone would have probably expected that whenever you immortalize any primary cells, they should become, in theory, sensitive to lipid synthesis because these cells now are actively dividing, they don't senesce, and they proliferate at a much faster rate than the primary astrocyte. However, that was not the case. There was no difference in sensitivity. The next step was to introduce oncogenic pathways that are known to be activated in GBM. For example, EGFR, truncated EGFR, which is EGFRB3, which is known to activate PI3 pathway. And we also introduced a RAS, which is known to activate magnetic nerve signaling. And to make a long story short, what we found is that whenever we activate RAS signaling, Now these tumors, now these astrocytes become sensitive to this therapy. Not only we see that at the cell death level, but you can see that in terms of the stress response. So the primary astrocytes don't upregulate any stress signal whenever they're treated with these inhibitors. However, now the HRAS cells, they do that. We confirm that through many different ways, but most importantly, we confirm that on the glioma stem cell, patient-derived cells that we have. Essentially, what we found is that there's a very strong correlation, R is minus 0.9 here, between the EC50 of YTX and the phosphorylation level of ERK. And what that means is that tumors that have the highest level of ERK are also the most sensitive to this therapy. Whenever we inhibit either MAC or ERK, not only these cells don't upregulate any stress response anymore when they're treated with these inhibitors, they also almost fully viable when we block these, ST. So we wanted to dig further into this. We know that GBM is very heterogeneous. And so the question you asked here, that there must be some subpopulation within any given patient-derived cell line, no matter how sensitive it is to this therapy, that are actually resistant to these inhibitors. So what we did here is that we treated sensitive cells, two different sensitive patient-derived lines, with an SCD inhibitor for about 6 weeks. Of course, 90% of the cells died, but then we had very few cells that we were able to expand, and we kept these cells under SCD inhibitors. So these cells, basically, they become resistant to this therapy, and these are defined as R here. And then when we compared ERK expression or ERK activation in these parental versus the resistant cells, what we saw essentially is that ERK is decreased. So what that means is that there are glioma stem cell subpopulation that have low MAC and ERK, and this allows these cells to escape this therapy. It is important to mention that these cells become not only resistant to the SCD inhibition, but they also become resistant to an inhibitor of the other enzymes that are involved in this pathway. So they become fully resistant to lipogenesis in general. Of course, MAC and ERK signaling is pleiotropic. There's numerous pathways or genes that could be activated through this process. So we wanted to know exactly what is happening. And what we found is that whenever ERK is activated, shown here, for example, is the astrocyte model, AMP kinase is actually inhibited. And AMP kinase is known as the metabolic sensor in cells. So essentially, whenever there's low nutrients, AMP kinase can sense that and get activated to compensate for that. The opposite here is also true. Whenever in these resistant populations that have low ERK activation, what we see is activation of AMP kinase to compensate for that. We proved that activation of AMP kinase actually fully protects against SCD inhibitors. This is shown one example here where we genetically activate a consistently active AMP kinase alpha 1 or alpha 2. And what we see essentially is that we can fully rescue from the toxicity of these inhibitors. We did that also in terms of pharmacological activation of AMP kinase, as well as physiological activation of AMP kinase. But what was really surprising to see is that this is not only happening whenever we pharmacologically inhibit SCD. If we knock down SCD, that's basically long-term inhibition of fatty acid saturation. As I told you earlier, knocking down SCD prevents tumor growth in mice. However, now if we activate AMP kinase and we knock down SCD, these cells are able to engraft in the mice, and these tumors can grow almost similar to the control. So basically what this tells us is that glioma stem cells can actually adapt to lipotoxicity, but also to fully impair lipogenesis by activating AMP kinase. Also, again, here, it's important to mention that this AMP kinase provides resistance not only to SCD inhibitors, but to all the other enzymes, PASA and ACC, and all of these are very well established cancer targets. So to finally try to understand exactly what's going on, why AMP kinase is providing this very strong protection, we ran shotgun lipidomics and looking at what is exactly happening at the fatty acid level whenever AMP kinase is activated. And what we found essentially, what you can see here right off the bat, those red don't increase, there's two subfamilies of lipids. What we saw is that neutrolipids are actually increased in the AMP kinase group, particularly two families of neutrolipids. One is the cholesterol esters, and the other one is triglycerides. They are upregulated by AMP kinase, especially whenever we combine AMP kinase with acid inhibitor. And it is known that these two lipid subclasses are precursors for lipid droplets. So lipid droplets essentially are these storage units that the cell have, where essentially they can store a lot of, it's essentially an energy source for the cell. Whenever there's shortage of nutrients, these neutrolipids can be activated or to provide energy for the cell. We actually were able to confirm that AMP kinase increases a lipid droplet formation. And to make a long story short, what we found is that whenever SCD is inhibited, as I told you, there's these accumulation of these saturated fatty acids that are toxic. However, when AMP kinase is also active, what happens is that AMP kinase shuttles these toxic lipids into these lipid droplets. So now not only the membrane integrity is preserved, but also now these cells have extra energy stored in these lipids that allows them to survive even when the fatty acid or lipid synthesis is depleted. So to put this into a clinical perspective, so what are the clinical implications of this work? First, we show the efficacy of a first clinical grade inhibitor of SCD. And this is important because this inhibitor is brain penetrant and it's been tested on humans. Second, we show that NAC and ERK, as well as AMP kinase activities, which should be detected by chemistries on tumor biopsies from patients, could be predicted biomarkers to guide patient selection as qualification. So basically, now we can know which patients cohorts are most likely to respond to this therapy. And again, that's I'm not only talking about SCD1 therapy, but also any therapy that could target FASN or other enzymes that are involved in this topic. And thirdly, we can optimize treatment paradigm to maximize therapeutic efficacy. So as I showed you, the combination of SCD with DNA damaging agent is definitely beneficial, especially temozolomide and radiation, standard of care for GBM. But also that lipogenesis inhibitor should not be combined with activators of AMP kinase. For example, two very widely used drugs, which is salicylate, anti-inflammatory, and metformin, anti-diabetic. So both of them activate AMP kinase. So patients who are undergoing this experimental therapy should not be taking aspirin or metformin. I will end here. I just want to thank, I mentioned some of the people in my lab who were involved in this work, but there's also other people who have done really tremendous work and effort. So I'm very lucky and fortunate to be working with them. Some of these present and past members are shown here. I also want to thank our collaborators, particularly Chi at Humanity, who was really very, very helpful in all the studies involving YTX. Steve Bensinger's group at UCLA for the tremendous help with the lipidomic studies. I want to thank Scott and Isabel because they were really, they helped me initiate this collaboration with Humanity. Hero for providing all the lines, GSC lines that we have, most of them in the lab, and as well as Charles, who is not only a great collaborator, but also a great friend. And I want to thank all our funding sources, and thank you all for this.
That's a great talk. Is there any way to stratify your studies like nerve stress and lipid synthesis so that you look not only at the biopsy, but the stem cells that activate dividing cells and see how, for example, activate dividing cells of glioma have the same level of ER stress as others.
So basically, is there a way to distinguish cells that have high or low ER stress in?
Well, in other words, I guess it's something like we feel both when we do maybe actively divide. You know, so the stem cell like cells inside the. So if you look at it, we only say, yeah, there's a lot of times of stress and a lot of pathogenesis. That may be true, and a lot of cells that may not be able to divide the stress, but there the other cells in there that the cells that you really want to know about, the cells that are actively dividing.
Yeah.
Is there any way to zero in on those guys and say, you know, what's their this is like, what's their stress?
Yeah, I mean, theoretically, it is possible. There's ways that we can look, for example, gene expression of cell cycle markers to know that certain cells are actively dividing. However, based on our data and other people's data, it doesn't seem to be the case that cells that are highly dividing or actively dividing are the ones that most dependent on lipid. Actually, there's even a study GBM where they showed that what they call slow cycling cells, these cells, obviously as they indicate, they cycle at a much slower rate than the general GBM population. They show that these cells are also highly dependent on lipid metabolism. So and also that's also proven by our astrocyte studies. So if we immortalize these cells, even though they start dividing faster, they don't become necessarily sensitive to stir. It's not only the cell cycle that's driving this sensitivity to this therapy. Hope I answered. Yeah. So the question is, what are your thoughts on apparent synergistic mechanism of YTX and PARP in triple negative breast cancer? Yeah, thanks for the question. So basically, as I mentioned, we did see that YTX downregulate PARP at the protein level. And whenever PARP is downregulated, theoretically, DNA damage is increased. So essentially, I believe that this observed synergy just because it's caused by depletion of the ability of the tumor cells to repair DNA damage, and at the same time, two DNA damaging agents combined together. So basically, increase in DNA damage. Let's see. I mean, this is the chat.
Yeah. Just like you said, they'll just communicate.
Yeah, I think that's it.
That's it, yeah.
All right.